Think of the physical world as a massive, predictable machine. At the human scale and out into the cosmos, objects obey a strict set of rules known as classical physics. These rules offer the promise of determinism. If you know exactly where a baseball is right now and how fast it's moving, equations can tell you exactly where it will land. By the late 19th century, that mechanical view of reality felt nearly complete. Then, a series of stubborn experiments forced a radical realization. As physicists zoomed in on the building blocks of matter, they hit a hard boundary line defined by a microscopic threshold called Planck's constant. Cross that line, and the familiar laws of physics simply stop working. At the scale of atoms, electrons, and photons, certainty vanishes. We step into the quantum realm, a place governed by shifting probabilities instead of fixed physical positions. This shift means that beneath the surface of our predictable mechanical world lies a subatomic landscape where every familiar rule of motion and location is rewritten. The strange behavior of this microscopic world starts with wave-particle duality. Until someone actually measures them, subatomic particles do not exist as solid dots in a single location. We can see this in action through the famous double-slit experiment. Fire an unobserved electron at a barrier with two slits, and it travels as a probability wave, creating an interference pattern on the wall behind it. But place a detector at those slits, and the wave immediately collapses into a single, definite physical point. This bizarre behavior leads to a rule formulated by Werner Heisenberg. His uncertainty principle states a rigid trade-off. The more precisely we pin down a particle's location, the less we can possibly know about its momentum. This limit isn't caused by clumsy laboratory tools or weak microscopes. It is an inescapable mathematical constraint built directly into the fabric of the universe. In the quantum world, observation is a trade-off. We can never achieve a complete, simultaneous picture of a particle's properties because uncertainty is woven into the mathematics of reality. Quantum tunneling takes this further. It allows a particle to hit an energy barrier it shouldn't be able to cross, and because its probability wave extends into the barrier, it can sometimes simply materialize on the other side. This effect is what allows the sun to shine. Without particles tunneling through energy barriers to smash together, nuclear fusion would be physically impossible. Then there is quantum entanglement. If two separate particles interact and become entangled, they share a single quantum state. Measure one, and you instantly know the state of the other, regardless of the physical distance between them. That instant connection violates classical logic so severely that Albert Einstein famously dismissed the entire concept as spooky action at a distance. Yet repeated experiments prove the connection is real. At its core, the universe is non-local and intertwined, operating on a logic that actively defies human intuition. This raises a massive paradox. If our foundational building blocks are blurry, unpredictable probabilities, why does the world around us feel so solid and reliable? The answer lies in a process called decoherence. As fragile quantum systems bump into their surrounding environment, they rapidly lose their quantum properties and lock into a single, stable classical state. Physical reality, as we know it, emerges from these rules. Thanks to the Pauli exclusion principle, certain atomic particles cannot occupy the exact same state, which is the only reason matter takes up physical space instead of collapsing. Engineers have moved beyond observing these hidden rules to actively manipulating them to build modern technology. For example, an MRI machine generates its detailed images by measuring the quantum spin states of hydrogen atoms inside the human body. And the semiconductors inside your smartphone or computer operate entirely on quantum behavior to direct the flow of electrons. The solid, predictable world around you is a macroscopic result of these interactions, a reliable interface built upon a foundation of shifting probabilities and engineered quantum states.